Good morning. Today we are going to work on a laboratory activity, the purpose of which is to see if we can confirm Newton's second law. What's going to happen here is we have the cart, as you probably can see on this, if it doesn't bounce around too much. So we got a cart. We have a hook. See the hook? The string is probably too narrow to see on the screen. I got a little tape here to bump that. There's a pulley here that allows this to go forward. So what we're going to do is we're going to turn on our Logger Pro, and it defaults and detects that there's a photo gate there, but it's going to think that it is the dropping exercise we did with the picket fence. So therefore, we need to tell it that we have a different sensor. So I open that up, as you can see here. I go to probes and sensors, double click. I come down here where it says photo gates, because that's what we're using. I'm using a pulley. I click on that, hit open. We're going to measure distance, velocity, acceleration. However, the acceleration will probably be too messy to see, so we're going to remove that. I am going to click this, move this part down, move this down a little bit, make this bigger. So this is easier to see. I'll leave the screen there so you can see what we're actually recording. I pull this back. We have 50 grams of mass hanging there, or 0.05 kilograms. Multiply it by gravity, 9.8, and it tells you how many newtons we're pulling with. We'll do that exercise in a moment here. So, let's see if I can give you a little bit of, hopefully you can see that a little bit better. And I hit collect, let it drop. Now if I hit auto scale, it makes this goes on. The quadratic fit of the position time graph. You notice I leave the ends alone because I have a slow acceleration at the beginning and I have that roll of tape at the end there, so I don't want the very ends. I want the middle 80%. If I hit the quadratic fit and I double it, it tells me what the acceleration is. This number here for the same time period should be very similar. And I take the slope of that, and if you look at it, they are very, very similar. So 0.7751. We'll do this 10 times. Then we're going to put on 500 grams with the mass. We have lots of different mass units that work about 500 grams. You'll double check them on the balance. What do you think is going to happen if I put more load on this? Faster or slower acceleration? We already know it starts at 0 and has an acceleration, so there's a change. So I'll click this off, hit collect, let it run, hit stop, and once again I'll collect that 80% as a quadratic fit, which tells me what's going on with the position and time. And you can see it's double, so the next number should be 4080-ish here. Let's see how well we do. 4077. See how the two numbers are very, very close? There's going to be a little bit of difference between the two, but allows you to compare does the data consistent with itself. Once you have this data, then you open up the spreadsheet here. Let me see if I can actually get this out of the way. One moment here. I got the camera in the way, but we can move that out of the way. You have a sheet of paper that looks like this spreadsheet here. Or you should. Here we go. Oh, great. I don't want draw and zoom. I want that gone. There we go. Yeah, there we go. So now we have this. You should have a sheet there. If you put in the mass, 0.05, that's where that goes on that sheet. Obviously, your name would go at the top, date, block. Here we put in the mass of the cart. When I weighed the cart, it was 514.7 grams, or 0.5147 kilograms. The weight I put in the top was half a kilogram. So the hanging mass goes here. That was this. Multiply it by gravity, and I got 0.49 newtons. the cart has a little bit of friction. It's about 0.05 newtons. So we do that, come here, and that means this minus this tells me the net force, because we're trying to figure out the acceleration. With the net force, I put that here, the amount of mass that I'm moving. You notice that it's this number plus this number, because can the hook fall down without pulling the cart, and can the cart move without that? And then the predicted acceleration is 0.0792. Now I've done this 10 times already, and we end up with the following results. And then we go along here, and I put the results in. Here's the average of them. The difference from the theoretical, that would be one number minus the other, is 0.046, which would be the amount of error there is. And we just do that the same way all the way down. Then we can do percent error, which is actual minus theoretical, this number here, divided by the theoretical, this number, times 100, and I get these numbers. So as you can see, we're very, very close. We have one reading that was a bit off. The rest of them were very, very close, within 5%. Of course, we're trying to stay within 10%. Now, when I put in the extra weight, what happens over here is I go back to here and I say, my theoretical, how much mass am I moving? I am moving this, which is this number. So theoretically, in perfect world, I should have 0.04133 meters per second. We took the data. Here's the numbers I have. How far off were they as just raw numbers? Was this, one minus the other. So it's this minus that. Now I take this divided by that times 100 and put it here and see how much I missed by. And you can see that I average under 5%. In fact, most of the time it's pretty good. I have one really screwy number here, but that's the way it goes. Now, based on the data, is Newton's second law confirmed? I.e., for example, follows the expected pattern within 10%, or is it not? Now for the rough question. Why do you say it does or does not follow? And that's the exercise for today, and this counts as a lab, but it's going to be the real shortest lab if you do it all during the class period today, and don't fight with me on this. And hopefully that'll answer some questions. If not, ask me again.